Proud privilege to be with you all for this wonderful function, starting the Earth Science Society in IDS. And IDS, we all know it is just not geology. It's a blended tool that we run. So obviously there's a strong interaction among various different disciplines, and that is what the new education policy also emphasizes. We shouldn't be get confined to our own subject, own discipline, but should also get some knowledge about the other areas also. And that is what basically has been talked about in the new education policy. In fact, in the preamble of that, there's a wonderful statement. It has been said that the destiny of the nation, destiny of this country, will be decided in the classrooms of schools and colleges. So obviously, it envisages more of a holistic development of student, and then all-round development means basically not getting confined to one particular discipline. Of course, you can be a subject expert in one, but multidisciplinarity becomes basically the basis of your education. And it's so good that under the blended BSc, in fact, we've been running BSc program in environmental science, earth science, chemistry, physics, biology. And when we speak about the planet Earth, which is the only living planet, there is no other planet like our planet. And when we speak about the planet, living planet, so obviously it has 4 different components also. The outermost sphere, we divide it into different spheres, as the outermost is atmosphere. Then the lithosphere, which is the uppermost part of the earth. Then hydrosphere, which takes care of basically our water part. And due to the interaction or the seamless interaction among all these 3, creates the 4th sphere, that is called the biosphere. So life exists only because the remaining 3 spheres are constantly interacting with each other. And that is what is the beauty of this particular planet. So when we say Earth Science Society, it doesn't necessarily mean only geology. It has become very multidisciplinary character. No, I am not saying interdisciplinary, it's multidisciplinary. So various different aspects in look at it. And therefore, according to, if you look at the various different sort of branches of geology, you would find a great connect with the other branches, whether it is physics, whether it is biology, whether it is mathematics, whether it is statistics, whether it is geography, whether it is even history. It's called archaeology, ancient history. And therefore, we should have a very wider perspective when we are actually working for this society. We should restrict ourselves only to the geology fraternity. It is for all. I tell you, being a geologist, spent almost more than 40 years in this subject and still continuing. It basically gives you an opportunity to wander around. Fieldwork is an essential constituent of geology, and that makes you travel to different places, understand different aspects, not only geology, the entire ecosystem that is around, the human culture, all different parts in fact. And that broadens your basically understanding about the entire society. I am going to actually also restrict to the topic of geology, but I am going to make it as simple because I understand there is students from liberal arts also sitting here, some students specifically coming from geology, from the campus, outside the campus, and so on and so forth. The thing that was mentioned by your head of department and my colleague, Professor Kumbhar sir, that we are actually graduating this 3 years degree program into 4 years degree program. Now the obvious question that arises in everyone's mind, what are going to be the tangible benefits of this? So along with geology, in fact along with your core subject, first of all, you can have basically opportunity to learn some other subjects also. There is plenty of flexibility being provided. 50% of your overall graduation program, it is of 3 years, that is generally in the range of 120 to 132 credits. So wherein in fact apart from your subject, some specific skills, discipline specific, as well as entrepreneurship related, then the value education, internship, experiential learning, and you basically get to know or get to have some hands-on experience. And that all together basically makes your degree. And the 4th year, it is left to you whether you intend to go for an honors course or you want to make it a research degree. The 4th year, obviously, you get introduced to the research methodology, and then doing a dissertation on a topic which is of multidisciplinary in nature, and that involves also some amount of internship. The idea is basically you get the best of the exposure, the best of the industry, the best of the mentoring from the best of the people. So when you come out after doing your graduation, 4-year graduation, obviously, it is expected that it would help you in creating your own livelihood. I'm not saying just employment, basically. Livelihood is something much broader, much. And then if you achieve, say, 75% of grades, then obviously that gives you an opportunity that without doing 1 year of master's course, if you wish, you can go for your PhD program, doctoral program. So you're actually saving on 1 year. And that is what is the sort of structure generally you get to see in most of the outside world other than India, especially in the European part, in the Western part. So generally when you after graduation you intend to do a post-graduation, you got to do some intermediate course there, so you'll be spending 1 year extra. That burden basically both economically as well as mentally also, because you'll be away from your family for 1 more extra. And then apart from that, basically you actually get to understand many other verticals apart from your subject. And that is what this 4-year degree course is all about. Provided you get 75% of your grades. And accordingly, it would be honors degree or it would be a master's degree in research. Then you have plenty of flexibility. You can, in fact, while doing geology, something that you like, perhaps which has been taught in the BA liberal course, that credit also came out. It is not necessary that when you take admission to Pune University for this particular course, that you would be restricting yourself to this 400 kilometers of campus. but you in fact have the flexibility and opportunity to acquire some courses, some credit from other higher education institutions, including those are in Pune and outside Pune or in the other states also. And that is what, in fact, we are planning out, like there will be for the state of Maharashtra, we creating a separate portal on which basically there will be a bouquet of courses provided, or rather would make visible to you and choices left to you, whichever you want to do. So that is the kind of a flexibility that we are speaking of. And therefore, I think the new education policy is going to be a game changer. And then along with that, along with basically the learning experience, obviously, there will be also changes in the way the evaluation, assessment and examination is done. So there will be a complete sort of a changeover in your examination pattern also, or the way the examinations are conducted. It would not be like the way that is happening presently as well, where actually what get tested, that whatever that you remember that get tested. It doesn't test you what you have understood, what knowledge you have, is it? So summative format. So there are ways and means on which in fact we are working on that. So, and that we intend to actually start it from the coming academic years 2023, 2024. In fact, I was told that some of you students who are in the third years and obviously have taken admission 1 or 2 years before time, so whether this policy encompasses you or not, it will, provided you will require to undergo some bridge courses or some additional sort of credits, so that even you can also join this 4-year degree. So in days to come, perhaps the modalities or the general guidelines, everything will be made visible to you all, will be provided to you all. And I'm pretty sure you certainly will get attracted to this new change and perhaps may get enrolled for your 4-year degree program. So with this, I'm switching over to now geology. And geology means basically earth. As I said, that earth is generally get divided, although it's a sphere, but if you take a cross section of it, you get to see number of layers. The uppermost on which we are living basically is the crust, and beneath that, as you start getting into the interior, obviously, both the temperature and pressure that starts acting upon us. And because of this change in temperature pressure conditions, obviously, the kind of material that we actually pass through goes on changing in its character, in its chemistry, in its mineralogy, in its all different properties as such. General management. Yeah. Not this. Mental general. Cut it. You get to see a different layer, and here you can see. This is the small thin layer on top that we call the crust. This yellow portion that you are looking at is called the mantle. And this entire thing, arc shape, is what is called as a core. And of course there will be further subdivisions of it depending upon its property, the temperature, the mineral composition, as well as the pressure. And then this mantle basically further get divided into upper mantle and lower mantle. Some portion of the upper mantle and the crust together makes what is called a lithosphere, that has two parts. Lithosphere, hydrosphere, atmosphere and biosphere. The crust again, as we see that there are two kinds of crust. One that you get to see onto the ocean floor, that's called the oceanic crust, which is distinctly different in its character. And the other one basically, on which we are living, is called as a continental crust. The basic difference being the continental crust is older. If you look at the age of the continental crust, the oldest rock that you get to see almost goes up to 3.5 to 4 billion years old rocks. So they are to a great extent basically are preserved on different parts of the earth, in different regions of the earth. If we have to consider only the Indian subcontinent, the oldest rock occurs normally to the south, Karmalkar, then maybe Tamil Nadu, maybe Andhra, all those areas basically. This is the oldest rock. And as we start moving from south to north, when you get into the Himalayan part, youngest rocks are exposed in the Himalayan regions. And then, why in the first place the age of the earth, age of this continental crust is so old? The reason being, it doesn't get destroyed. Again, that the oceanic crust, whenever it gets formed, it is destined to get destroyed through processes of subduction. We come to that a little later. As two continental landmasses collide together, so obviously the intervening oceanic basin gets subducted, curves downward, and actually gets recycled back into the interiors. And therefore oceanic crust rarely get preserved. The oldest oceanic crust that we get to see is of Jurassic age, 160 to 140. That is the age range basically. Again, the oldest continental crust, which is 3.5 and beyond billion years. So that is the difference. And why the oceanic crust gets subducted? Because it is more denser in character. So, and density to a great extent is given by its composition. So it is composed of more denser material, denser minerals, and the minerals include basically iron rich and magnesium rich minerals. And I'm not getting into the plethora of names and all that. I'm making it simple for those who actually are from liberal arts. So I'm keeping it very general. So density to a great extent decides the fate of these rocks. So once one gets destroyed, the other doesn't have to. So compositionally, on the basis of composition, we can have three divisions: crust, mantle, and core. The crust, obviously, as I said, two kinds of crust: oceanic and continental. Oceanic crust is more denser, more MgF rich, as against that basically continental crust, which is more felsic in character and has a lesser density. The mantle basically is the material which in fact is running this entire planet as such. We call this is a dynamic planet. There are movements happening, there are earthquake happening, there are volcanic activities happening, and so on and so forth. That is all because of basically the presence of the mantle, which is very hot. So it's like basically the energy that is required to run an engine comes from this particular portion, that is the mantle part. So since mantle is hot and is neither liquid nor solid, it is semi-liquid or semi-solid in its composition of this, more rich in Mg and more rich in Ap, and from where basically we have the generation of magma, generation of volcanic activity. Whenever there is volcano, obviously there is new addition of material to the continental part. The volcanic activity is a common feature of the ocean floor, but since it is out of sight, we don't see it. But it is a regular activity that is happening in the middle part of the ocean, where in fact there is a huge long fracture or a mountain range, we can call it, as height-wise, basically like any other mountain, Lake Himalaya. So that's all is happening basically because there is a continuous production of new crust, new oceanic crust that is happening. And then you get into the core part. Core actually then get further divided into two. The innermost core is solid, the outer core is liquid in composition, and generally made up of alloys of nickel, iron, and Pn. So this is all about basically the compositional part, rheology. So depending upon basically it is, whether it is elastic, whether it is plastic, whether it is solid, that is called the rheological definition: lithosphere, asthenosphere, and mesosphere. The lithosphere is more ductile in character, basically it gets brittle in character. The asthenosphere is more ductile, and mesosphere is further down. So which get decided by basically temperature, pressure conditions. Same picture. Now we can in fact look at the complete cross section of it. The inner core, the outer core, the lower mantle, the asthenosphere, and the lithosphere, which makes more or less the upper part of the mantle and both the continental and the oceanic crust. When it is oceanic crust plus mantle, it is called oceanic lithosphere. Continental crust plus mantle is called continental lithosphere. And then over here, basically, you can see this is what something that is going inside. This is the process of subtraction. So two continents colliding, and then because of the density, this whole thing is getting down, curving down, and gets subtracted. And that is what generally happens with the oceanic crust. So oceanic crust rarely get preserved, get destroyed, and that's the reason you have a very little of old oceanic crust preserved, just Jurassic material. And then obviously on the basis of the rheological boundary or temperature pressure conditions, obviously there are different boundaries being demarcated. So we will not get into that jargon of nomenclature, what this thing. So these are some particular definition. Crust versus mantle. The crust is the product of mantle melting. So obviously where from the crust has come? Whenever there is volcanic activity, new material gets added up, and that's how the crust gets formed. So it is actually coming from basically the mantle. So the mantle is the reservoir of all kinds of igneous or all kinds of volcanic activities. So from there, in fact, everything is thrown on. So whenever mantle gets melted, mantle as it is near to its melting point. So when you intend to melt something, two ways you can melt a particular material: by raising temperature or by dropping the pressure. The effect would be seen. So here most of the time basically it is dropping in pressure. The mantle being buoyant in character needs to its melting point is always popping up, but it has been constantly being compressed because of the overlying load of the lithosphere. But when the lithosphere gets ruptured, so there will be loss in pressure, and to fill in that gap, the mantle will actually rise. So when it gets into upper regions, obviously, the temperature drops, but not substantially, but there is a substantial drop of pressure, and the melting begins. And that's how actually the volcanic activity starts happening, like the Hawaiian islands that we look at. So on day-to-day basis, this activity that is happening, or sometimes even in India, in the Andaman part, basically, there is volcanic activity. Presently, is dormant, but sometime like few years before time, it was quite active as well. So that is how the mantle basically is the reservoir. Whenever it undergoes melting, it produces magma, and the magma starts its movement upward. And when it comes upward, obviously, it produces different kinds of processes. So the only way of understanding the interior of the earth, the only proxy that we can make use of is the rock. We cannot take a trip to the mantle. Even the drilling is not feasible. You can drill almost up to a depth of say 8-9 kilometers, not beyond that, because the pressures start playing its role. So we have no machines to drill down to a depth of say 20-30 kilometers. Okay. So this is limited. We have a limited access in that. So the only material that is available on the surface is the rock. The rock is basically, you can make use of it as a proxy to understand the characters of the earth interior. But sometimes it so happens that when this magma is coming up, if it is coming basically with a tremendous speed, it may break open or rather collect some pieces of the mantle, and they will be brought up onto the surface. They are called as zinnels. They are called zinnels. There can be crustal zinnels and there can be mantle zinnels. So sometimes the fragment of this mantle are brought to the surface, and from that you can understand. So they have not undergone any kind of basically modification. They are as it is being brought to the surface. And then that provides you an opportunity to understand about the mantle composition. But it is restricted to a depth of say, the deepest zinnolith that is so far been recovered is coming from a depth of 350, 400 odd kilometers. But the mantle is further deep. Almost it goes to the outer core of it. And for that, obviously, there are different ways. Then we have to actually depend upon the indirect means, the geophysical methods that we make use of, the magnetic or the gravity, maybe basically the seismic properties. So whenever earthquake happens, perhaps it is disastrous, but for a geologist, obviously, it gives you an understanding about the various different things that are happening in the interior. So the seismic studies to a great extent tell you about seismic plus some lab experiment that we perform, and based on which we envisage that probably what could be the characters of that particular material. Then other important material that actually also gives you an understanding about, or rather helps you in unraveling the mysteries of the Earth's interior, is the diamond. So diamond basically may be for the entire world, they are what we call them gem quality rocks. They enhances everybody's beauty. But actually for a geology person, the microscopic inclusions are seen present in the diamond, which are coming from a depth in excess of 600 odd kilometers. And then sometimes in the form of fluid, sometimes as solid inclusions. And when it is in solid, obviously, it's the direct material being brought to the surface from a depth of more than 600 odd kilometers. So you understand, like with temperature and pressure, what mineralogical changes are happening. Okay. So that you can understand on the basis of the sublithospheric inclusions that you get to see in the dimensions. I will not get into all this basically minute details of. So when we look at the composition part of it, generally we actually look at the rock in its composition. Chemically it is actually made up of 10 major oxides. So it's silica, alumina, iron, magnesium, calcium, there could be titanium, there could be nickel, there could be P2 or potash. Into all that makes almost 100% of its composition. So depending upon basically whether the Mg is more or iron is more, rocks are further divided into different categories: basic, mafic, ultramafic, acidic. Okay. So based on basically the ratio of silica and magnesium acidity. So the average component based on analysis of mantle relief. Now here we are speaking about the mantle part, not the uppermost portion, but the crust part. But any composition of rock actually gets represented in the form of 10 major oxides and some elements which are to a great extent occur as in minor quantities or in trace quantities. Parts per million, parts per trillion, parts per billion. That makes up almost 1.5% of the total composition of the rock. So 99% it is made up of these various oxides. But these are subjected to change whenever the rock basically undergoes any alteration, any weathering, when it gets attacked by the various elements of the climate, maybe the water, maybe wind, maybe sun, so it gets decomposed, and therefore this composition is the composition get changed considerably. So this composition basically doesn't help us in understanding. The geologists, basically most of them, they work for understanding the origin of the rock, how this rock is originated. And to understand that genesis aspect, many times these elements which actually are subject to change and therefore cannot be of value. So you have to depend on basically those elements which do not get changed by any physical or any mechanical or by any chemical process. Those are generally are the minor or trace elements, what we call them as rare earth elements. They do not get changed. So basically we actually look into those elements and then try to unravel the process of rock formation. Okay. So SiO2 over here you can see the MgO content, magnesium is 38%. Again that FeO, basically is low and the SiO2 is 45%. So you have silica and you have magnesium. These are the largest oxide content present in. But since silica is common to all rocks, if the magnesium basically decides the nomenclature over here, and the major oxide to a great extent can be of use in giving a name to the rock. So this is actually called as ultramafic. The overall basically material is generally called as a family name, peridotite, and there could be subfamilies under that, and those are basically different names that we call them as lazulite, verolite, dunite, Habsburgite, and so on. Okay. So we will not get into those details again. So upper mantle extends from Moho to a depth of 660 kilometers. 660 kilometers is what we call a seismic discontinuity. So in fact we get to see a change in the seismic properties. And why does it happen? Because as I mentioned previously, the oceanic crust, which is destined to get destroyed, destruction means actually it is getting recycled back into the mantle. And that journey has been traced on the basis of the geophysical means or geophysical studies, how deep the oceanic crust goes down. So we could track the journey up to depth of 660 kilometers. Beyond that, we do not understand what happens to the crust, the oceanic crust. Perhaps the temperature is so high that it gets leveled up over there, it gets completely mixed. Or perhaps the density is so high that there is no further subduction possible. We do not know that basically what exactly been happening as well. But generally, the rocks on the surface and their chemistry and their mineralogy sometimes lead you to understand about what has happened to a greater depth. Whether there is a mixture, the oceanic crust is completely admixed, completely basically got mixed up, homogenized, or sometimes it is being dissolved maybe in a minute quantity, and then whenever there is a new igneous activity happens, the interior again resurfaces back onto the surface also. So that is how you actually understand about the very different processes that are operating in the interior as such. Okay. I spoke about that, like basically we are dividing the interior into various different boundaries, and these boundaries to a great extent depend on the compositional diversity as well. So the olivine, pyroxene, spinel, garnet, Mg perovskite, Mg wustite, these are the magnesium minerals. So olivine is stable almost in the upper part, on both olivine pyroxene in the lithosphere as well. Up to a depth of 60 km, the spinel is preserved. Beyond 60 km, spinel get destroyed and get transformed into a different form, is called the garnet. So beyond a depth of basically 660 kilometers, it further gets converted into a different form, Mg perovskite or Mg wustite. And all these minerals actually been studied as sublithospheric inclusions in diamonds. So diamond in fact provides us as a window to peep into the deeper portion of the earth. This is another concept, convection. Convection currents, we all know that when there is a temperature contrast, so the colder material actually gets moved down and the hotter material always comes up. We are quite actually familiar with this, and whenever even we heat the water, obviously the heated water generally floats upward, and the colder water, which is more denser, goes down. That is how exactly, because of the temperature contrast, this particular process is in operation. There are convection current basically, because the Earth's mantle is very hot, and therefore due to the convection activities, some portion of the mantle is risen up and some colder material actually goes down. This kind of convection cells are constantly operating in this interior part of the process. I spoke about the subduction process, that is how the oceanic crust actually gets subducted, and over here you can see this is the boundary 616 % discontinuity. So we do not know what happens to the oceanic crust. If you look at the figure also, it more or less stops here. Okay. Now this is the general classification of rocks, which is common to basically the geology person. You are quite familiar with this. There are different types of rocks. We call them as igneous, generated out of fire or magmatic activity or volcanic activity. Sedimentary, when this igneous or primary rocks are subjected to weathering, erosion, so get broken by mechanical processes, by change in temperature, pressure conditions, or there can be change in the chemistry, chemical decay, and then smaller particles get travel basically through lakes, rivers, streams, and finally get emptied into the ocean basin. Is it not? So there actually you can have deposition of this finer material. Those are called sedimentary rocks. And both igneous and sedimentary, when get buried by earth-shattering processes, when there is a upheaval and sometimes basically there is a downward journey. So they are again subjected to change different temperature pressure conditions, and accordingly to actually get adjusted with the changing temperature pressure conditions, the original mineral get transformed. Is it? That is what human being also does. When suddenly you got to travel to Himalaya, you take some warm clothing. Is it not? That's kind of transformation that you undergo physically also. So here basically rather than getting completely extinguished, it transformed into a different form which is stable to the new temperature pressure condition. Those are called the metamorphic process. So it's a solid transformation without the aid of any liquid materials. And there is another term that is called metasomatic, metamorphic and metasomatic, where fluid is playing an important role. There is some water, there is some fluid, which is to a great extent assisting that mineral to get transformed into a new species. So these are the common terms as such. I will not get into these mining details as such. We are actually more interested in the mantle part, and mantle obviously is made up of only three minerals: olivine, pyroxene, and perhaps spinel or garnet. The pyroxene again are of two types: lino and ortho. One which are crystallized in orthorhombic system, unmoving system, lino, and ortho, and olivine. And then, as I said, basically the alumina and chromium actually gets preserved in the form of spinel. This is the fourth mineral, which is third mineral, which is called the accessory mineral, which is stable up to a depth of 60 km, and beyond that it gets transformed into a garnet. Okay. So those are basically the minerals which, in fact, if you look at this particular diagram, this is a triangular diagram. You can see the olivine is at the apex part of this triangle. Here is the OPH, here is CPH. So over here it is 100%, and when you start moving toward this side, the percentage of it goes on decreasing. So it is 0 over here, from 0 to 100, from 0 to 100, from 0 to 100. So whenever you actually study a ultramafic rock or a peridotite, and how do you study it? Making a thin slice of it, you make a thin section, put it under a microscope, identify which particular minerals that are present, and then measure the volumetric proportion basically that is present. And that volumetric proportion is actually plotted in this particular triangular diagram, based on which there are certain various divisions being made. So the major divisions, as I said, dunite, lerzolite, and harzburgite and verolite. Okay. So depending upon basically the proportion of mineral which is particularly dominant, the classification gets changed. When it is completely monomineralic, entirely made up of olivine, it is called as dunite. When you have all the minerals present, that is olivine, pyroxene, clinopyroxene, both kind of pyroxenes are present, it is called as lerzolite. Then the clinopyroxene is absent, and you have only orthopyroxene, it is called as harzburgite. When orthopyroxene is absent, clinopyroxene dominant, it is called verolite. olivine is absent, only the both pyroxenes are present, is called a websterite. So that is how basically the rock get classified, the nomenclature. That is what we do based on basically the volumetric proportion of the mineral that is present, which you can actually see in the microscope. And this is how basically under microscope you get to see sometimes some minerals which are not actually common. Commonly seen like, as I said, olivine and pyroxene. But sometimes I get to see some minerals which are uncommon. I call them as foreign minerals. They are foreign entities sort of like flugopite and richterite. I mentioned previously that sometimes the fluid assisted sort of a change produces new minerals. These are actually hydroxyl bearing mineral phases. So wherein water is an essential constituent of their mineral structures. So those are richterite and flugopite, and that actually makes me understand a change that is all governed by or has happened because of addition of some water. That is a metasomatic process operated. Okay. So these are the four rock types I mentioned about: lazulite, halbulite, limonite, and berylite. This is how they look under microscope. This is actually the red thing that we are looking at is a spinel, and whenever in a plane polarized with light, basically the rest of the minerals they remain more or less colorless. But when you actually see them under cross metals, you get to see some color generated that makes you actually, or rather helps you in identifying the mineral species as well. Okay. So these are the pictures that we get to see of the rock when it is cut into a small sort of a slice and observed in the microscope as well. This is how basically these are some of the pictures taken in the microscope, and we are trying to actually make you understand the mineralogical diversity based on which the classification is done. Okay. So these are some of the pictures, and those are the common minerals that I talked about: olivine and pyroxene and spinel and manganese. And these are some minerals which are, I call them as foreign minerals: flugopite and pergasite, that is amphibole basically. Amphibole again is a water in its structure basically. Water is an essential constituent. So addition of water, a fluid assisted sort of a change in mineralogy. This is a metasomatic process. So metasomatism to a great extent sometimes adds new minerals, provided the fluid and rock ratio, the fluid ratio is higher, then only you get to see formation of crystallization of new mineral species. If the fluid and rock ratio is lower, perhaps you get a change in the chemistry, new elements are getting added, but no new minerals are found. And that is how basically the chemistry is a robust tool to understand sometimes or unravel these various different mysteries that have happened in the Earth's being. So I will not texture basically. I am just introducing you to the term texture. It is the architecture or the manner in which the minerals are arranged. So whether they are sharing common boundary or one is getting into the other, whether there is interaction that are happening. So all those features are observed first, and based on basically these textures, when you study basically or you are actually interested in knowing the genesis, that is you have to go in stages. First of all, collection of the rock samples from the field. You understand the field characters first. Then you make a thin section, put it on a microscope, see the basically mineralogy. Third, obviously, is the chemistry. Within the chemistry, again, there are Sub-verticals like understanding the stress element, understanding the isotopes, and finally the age part. And that is how actually we help you in understanding or putting into perspective the overall formation of that particular rock mass, which to an extent again governed by a major geological process. So overall actually a small piece of material actually telling you a good amount of basically story about the entire process of Earth evolution. So that is what is more important actually. Okay, so I will not get into this. Sometimes, in fact, within the minerals also you can have certain optical changes as over here you can see whenever you rotate the stage, every mineral actually gets into extinction. Extinction in the sense it completely becomes dark. So at fourth position it goes darker. But there are some minerals they do not go completely dark. Okay. In fact you get to see them in a small portion of it is an extinction, the middle portion is not still translucent and the other one is still not. So likewise, in fact, you can have a different sort of zones, and this is happening again because of the pressure that is operating. The mantle, you are looking at the mantle material which is subjected to basically the pressure. When it is coming from, even when it is traveling from deeper surface to upper, so obviously there is some change that is happening in temperature pressure. So that brings in some change in the mineral properties or optical properties. So they are of also importance, and like therefore they are studying great detail. These are generally what are called the king bands, kinking or bending of a mineral phase, and then they can be of value because they tell you about basically you can understand the stress, value of stress which actually has caused this particular change can be actually calculated. Means you can understand the pressure that operated upon to bring about this particular change. Okay. So the value stress estimate can be done on the basis of these very different minerals. And then coming to the chemistry part as well, I'm basically speaking about the trace element, not the major oxides, which actually are arranged in this particular diagram. You can see them most incompatible and less incompatible. On the basis of compatibility, in fact, these trace elements are arranged. So over here, most of them, what I call them to be HRE, heavy rare earth elements. In the middle part, generally what we call the MRE. Then light rare earth elements. Then you have basically based on their affinity, particularly to particular lithophile elements and so on. So different kind of distinguishing criteria are there. So accordingly, you arrange them. And then, on the basis of basically the incompatible elements, this incompatible element, those that partition into magma, compatible elements in crystal phases. So some minerals, whenever the mantle undergoes melting, some element prefer to get into the melt, and some element get retained into the mineral. So which are compatible, which are incompatible, and basically their ratios to a great extent will help you in understanding the overall process of melting. At what pressure, at what temperature, what amount of melting has occurred and how much of a mantle is involved in the melting process. Understand the word partial melting. It is not complete melting. Any portion of the mantle always gets melted partially, not completely. Okay. So whatever liquid that has been derived, basically a melt that is generated, is immediately sucked out in the form of the volcanic or magmatic activity. And then This is how actually the compatibility incompatibility criteria has been made use of in what is called as a truss element modeling. So on the basis of the truss element, there are various different ratios. We try to understand what is the process, what is the amount of partial melting, at what depth, at what temperature. All that extent can be understood, and based on which, in fact, you create a story. In fact, you understand the overall genesis of it. So this is how. This is the original rock in the central part. So that is the original rock being melted. When it undergoes partial melting, the melt that is generated, which actually producing a new rock, the chemistry is distinctly different. Is it not? So these elements actually have gone into the melt. And from the original rock, since they have gone into the melt, obviously, they are deducted from the original rock. And therefore the residue that is left will show a pattern depleted in those elements. So this is how basically you can in fact see a mirror image of these two curves, a mirror image of basically the original. Then depending upon the melting, so you can see 10% of melting, 50% of melting, 100% of melting. So all those modeling basically helps you understand the entire process. And coming to the last part, maybe after this I will show you some good photograph, nothing beyond that. So I will not bore you more. So over here you can see whenever the melting happens, the melting generates generally at the boundary part. That is the reason I said partial melting. It is not the entire mineral is completely getting dissolved. In fact, the minerals are generated here over here at this particular junction as well. Is it not? And then it is actually, so this is the original rock with increasing melting effect. You can see this network is getting widened, nothing beyond that. You don't see the entire portion is getting into the melt. Okay. So we switch over to the next, and then in 10 minutes I will finish off.